All right, Calc 3, welcome in. It's Thursday, December 2nd, and you've made it. This is the last video of the semester, last class of the semester. And it's good because we are near the end of stuff. I got one thing to do in 15.2, then we'll cover 15.3, and then we do one problem in 15.4. That sounds like a lot, but it's actually not too bad. So let's get started. The first thing I'm going to finish off in 15.2 is yet another form of the line integral. Now, last time we worked with the integral along a curve C of a field dot dr. Right, that was our symbol for the sort of conceptual way of thinking of a line integral. It's a force field or a vector field of some sort dotted with the differential of position, dr. Right, and we had other ways of thinking about this. The other one was what? We could think of this as f dot t dt, right? Something like that, yeah? And so we had different notations that describe the same thing. Well, there's yet another notation for this, and this one is useful because sometimes parameterizing a curve in terms of t is annoying. Sometimes it really is. And so we have a third form that's going to show up here, and that's called differential form. So let's talk about the line integral in differential form. Then we'll do an example where that's actually really quite useful to think of it that way. All right, so I'm going to do a little derivation here. It says f dot dr. One thing we can do is take apart what dr means. Well, dr means the derivative of r, dr dt with respect to t, times the differential of the independent variable, which is t, because r is a function of t. So dr unpacked as its differential is the derivative of r with respect to t times the differential of t. So that can get replaced with that way. Oh, let me now give us some information about the field. Suppose our field has, and I don't know why they use these letters, but it's very traditional. Say that it's some function mi plus nj. And they use capital M and N all the time like that. And let's say that the position, the r of t, is some x of ti plus y of tj. Sort of forgot the beginning part here, right? So we have a field, two-dimensional in this case, with components of m and n. These are functions of time, right? Or sorry, these are functions of x, y, I should say, functions of position, x, y. And r is a function of time, the parameter t, x, and y there, like that. Okay, now, let's sort of take this actual dot product, right? So what I have here is that this is the integral along C of f. Now, what is f? F is the vector mi plus nj, right? Dotted with the derivative of r with respect to t. Well, the derivative of r is just simply the derivative of this, right? So there's going to be x prime of t, I, plus y prime of t, j. And then the dt is still hanging out like that. And technically speaking now that this is a dt integral, I should really now, it's no longer along the curve, but rather it's from some parameter value a to some parameter value b. So yeah, so now I've gone from dt, so it's from a to b, some t equals a to some t equals b. Okay, now I'm actually going to do this dot product. This is going to end up giving me an integral from a to b of m times x prime, right? Which is dx dt, okay? And then plus n times dy dt, okay? And all of that times dt, right? Remember, a dot product of two vectors is a scalar and not a vector, yeah? So we have that. But now the dt can distribute, and it cancels the dt down there. And so this is often one of the forms that we can use. We'll say that this is the integral along the curve C, and it's going to be back to the curve C because the t is sort of canceling out. M dx plus n dy. This is the third form that we have for the line integral. This is called the differential form. The x component of the field sits here, and it's integrated with respect to dx. Then the n component of the field is here, and it's integrated with respect to dy. And so that is one way to think about that. Now, like I said, one of the reasons why this is super helpful can be like doing a problem like the following. So suppose here I want to evaluate the line integral along a curve of y dx plus x squared dy, where c is the arc given by y equals 4x minus x squared from 4, 0 to 1, 3. Okay. All right. So if I was to graph this curve, right, this is going to be an upside down parabola, and I only care about the arc from, a certain point to a certain point, right? So graphing that on GeoGebra or your graphing calculator, right, I know it goes through 4, 0 because it said so, right? So 4, 0, so I know it goes through there, and I know it goes through 1, 3. So I go ahead and put that dot down there as well, right? And then, if I want to plug in a 2 to figure this out, I'm going to get what? 8 minus 4, which is 4. So 2 is up here. And then 3, 12 minus 9 is 3. So it's back down again. So yeah, so I get the curve, the particle sort of goes along this parabola like that. Okay. See that? Like that. Now, if this was in a traditional sort of form as we had yesterday or the last video we had, I would now be very anxious to get this parameterized via t. Remember, we did c1, and then we had to say what x was and what y was, and parameterizing that. Well, here, what's nice is just follow your notation, and it'll actually walk you through how to do this. So, for instance, the path is called y equals 4x minus x squared. If I was to take the differential of both sides, well, then all of a sudden I'd have a description of dy and dx. See that? So what I can do here is take the differential of this, which is the differential of y. The differential of this would be its derivative, which is 4 minus 2x dx. And so I have a relationship between the dy here and the dx here. In other words, I'll be able to sort of plug in this dy, and now I'm back to a standard, regular, good old-fashioned Calc 1 integral. That's with respect to a single variable, dx, with respect to x. Okay, so let's go ahead and plug that in and see what we get. So this line integral along c of y dx plus x squared dy is going to equal the integral of, well, what is y? Y is 4x minus x squared, right? 4x minus x squared dx, right? That's this part here. Right? And then that's plus x squared, so x squared's good to keep, dy, but dy is 4 minus 2x dx. That. And since I'm doing this integral, I can really, it's the sum of two integrals here, but I can really think of it as one because this is integrating with respect to dx. This is integrating with respect to dx. So I basically like factor out the dx. And so now I'm working with 4x minus x squared plus 4x squared and minus 2x cubed dx. And then from what to what? Well, the x values, right, go from, they start at an x value of 4, and it goes until I go to an x value of 1. So weirdly enough, this is going to be an integral from 4 to 1. It feels backwards, doesn't it? We're used to putting the smaller number down here. But we have to respect the orientation, right? The orientation says it starts here and goes to there. So it starts at x equals 4 and goes to x equals 1. So anyway, now I have a little bit of simplifying to do here, but that's going to be just a Calc 1 integral. Not bad. So do you see how I followed the notation? I have this connection between y and x. So that gets me a connection between the differential of y and the differential of x, which allows me to plug this in terms of all just x stuff. And so I can convert this line integral to a single integral with just x stuff. Okay, I'll skip the actual calculation of this, but it's not too bad. But evidently you get 69 halves. Okay, and that finishes that off. Okay, awesome. Now that finishes off 15.2 as well. So let's get to, I don't know if I prepared my, yep, it's still showing stats. Hold on. One day this semester I'll get it. Oh wait, today's the last day. Let's get the Calc 3 textbook up here. Again, to save some time, I'm not going to calculate these, but I do want to show you 3 examples, and I want to note the final result in all 3 of them. Okay, and so I want to do this rather quickly and not have to worry about the actual calculation here. Okay, let's see here. Yes. So here we have 15.3, all about conservative vector fields and something called independence of path. All right, as you might have noticed, whether if you've done homework yet or not, you might notice that line integrals can be a little challenging because you have to parameterize the curve or have some description of that curve. Well, take a look at this example here. We have a force field here. Right, and they want to find the work done by this force field. So here is our field. Now they want to find the work done that on a particle that moves from the origin to 1, 1 along 3 separate different paths. Okay, the first one they want to just go straight there from this to there, straight line along the path y equals x. Okay, that's the first journey. The second journey is same start, same end, but now go via this parabola, x equals y squared. Then they have a third option, and they want to go from same start to same finish, but this time along the path y equals x cubed. Okay? And they go ahead and separately do these, right? So you do what we did last section. You have to now, okay, so this is y equals x. So you're going to come up with a parameterization for that curve, and then you plug in all the stuff, right? And you calculate, and you get 1/4. Okay? Well, they do that problem again. They get a parameterization for the second path, which is right here in part B. Okay? And then they go ahead and do that work integral again, calculate, they get 1/4. Then, on the third path, they parameterize this path, do the integral, and they get 1/4 here. What they didn't say, did they say this right away? Oh, okay, yeah. Notice the first thing they did, they say, hey, notice something here, that f is conservative because it passes that conservative test, right? So remember that how that goes? You take the derivative of this with respect to y, right? Which is going to be 1/2 x. You take the derivative of the j component with respect to x, which is going to be 1/2 x. And if these are the same, then that field is conservative, which by definition means there exists a potential function, a little f function, associated with that field. But they are also noticing that, at least on these 3 pieces of evidence, that in this conservative vector field, it looks like the work done is 1/4, 1/4, 1/4. The work done by the conservative vector field is the same for all 3 paths. Is that a coincidence? Is that something that we can exploit? Is that something we know happens because of conservative vector fields? That's the next question, of course. And then, after all that, remember this is a conservative vector field. And so there exists a little f, whose, when I take the gradient of this, gets me the vector field. So suppose I found little f. Look what happens when I plug in the ending point and then subtract the beginning point. So at the beginning point, right, I'm at 1, 1, right? Now, what is, when I plug in 1, 1 into little f, I get 1/4. When I plug in 0, 0, I get little f is 0. So it looks like when I take this difference, I also get 1/4. This is not a coincidence. This is an analog to the fundamental theorem of calculus. You might recall in Calc 1 that a definite integral can be evaluated at just the a point and the b point, right? Let me remind ourselves of that, right? In Calc 1, we said that the integral from a to b of capital F, right, like this. No, that's, I think they use little f here. Little f of x dx, like that. This equals capital F at b minus capital F at a. And where capital F is an antiderivative, right? That's the fundamental theorem of calculus right there. And so the fundamental theorem of calculus says if you can find an antiderivative for your function, this integral from a to b of that function, simply only the endpoints basically matter. This fundamental theorem of line integration that I just showed you here is the complete analog for line integration. Do you see in this case, it appears that the endpoints are the only thing that matter. Everything else about the journey doesn't matter. It's the start and the end. See that? So let's go ahead and write this out. Now, so this, what this turns out to be is a very practical shortcut. If, and this is a big if my field is conservative. Remember how I've been saying that the gradient is like the derivative, and the conservative vector field is saying what was like the antiderivative function, that little f that it came from. And so you can see that the analog is here. In a conservative vector field, we know there's an existence of this antiderivative, this little f, this potential function. And so this is the exact analog of the fundamental theorem of calculus. Let's go ahead and write this down, and then we'll actually do some very practical uses of this in calculating line integrals. We're going to rejoice because we don't care about the path in these cases. You know, the path can be super complicated. Doesn't matter. You just have to tell me in a conservative vector field where it starts and where it ends. That's all that matters. Yeah. And by the way, this has, good use in physics with the conservation of energy, right? The way that kinetic energy works, the way that potential energy works, right? And so, yeah, this connects into all of that stuff. So here we go. Fundamental theorem of line integrals. Let C be piecewise smooth. Curve, okay, lying in some open region R, given by some R of t, which equals x of ti plus y of tj, where t goes from some a to b. Okay. If a vector field f of xy, which equals, let's say, mi plus nj, like that, is conservative in R, okay, and m and n are continuous. That's basically so they're defined and nice like that in the region R. Then the line integral along C of f dot dr, that's the beast we've been calculating, right, is actually equal to the line integral of the curve, along the curve, of the gradient of little f dot dr which then equals, and this is the miraculous part, f at the endpoint, x of b, y of b, minus f at the starting point, x of a, y of a. Okay, where little f is a potential function. Of capital F. Okay? In other words, i.e., f is the gradient of little f. This is huge. This says that this line integral, all that matters in the calculation of this line integral, in the special case where the field is conservative, I only care about 2 points on that journey, the ending point and the beginning point. I do have to do some work to find little f. So I do have to calculate little f. Just like in Calc 1, you had to calculate an antiderivative, right? You couldn't just sort of plug in the b, plug in the a. You had to calculate an antiderivative and then plug in b and a, right? Here is the same sort of deal, except I would argue that maybe finding potential functions is a little bit more than just finding an antiderivative. But I hope you see that that's an analog, right? That this is totally sort of just an analog to that process in Calc 1. Right? Nice. Let's go ahead and do an example that uses this. Okay. So here's how this will go. We have an example here. We have a field, and it's 2xyi plus x squared minus yj. Okay, that's the field. And they want us to evaluate the line integral along a curve C, f dot dr. Okay? And here's how they've described C. They showed a picture. C starts at -1 to 4, and it goes to 1, 2, okay? And it looks like this. Okay, so let's get this on here. -1, 4, right there. 1, 2 is there. And here is the curve. It does this. How about that? Are you out of your mind, right? This is what you would be thinking is, right, is I have to parameterize this curve? I don't know how to do that. So this brings us to some options. It's like, well, okay, either this is going to really suck calculating this because I have to parameterize what this curve is, or maybe I should check, maybe I'll luck out. Ask yourself, is the field conservative? Because then if the field is conservative, we have options that greatly simplify this. Okay, so my first check is going to be, is this thing conservative? Now we know the answer is yes, because if you're keen memory, if you remember this from a couple videos back, this was an actual example that we did earlier. But I will remind us that it's a conservative vector field. F is conservative. Why? Right? F is conservative since the partial with respect to y of the first thing, that's going to be 2x, and the partial with respect to x of the second is 2x. These are the same. And so, yes, F is a conservative vector field, and now I don't care that the path is so complicated. As long as it's piecewise smooth, I'm good to go. I'm good to go, because all I care about is where it starts and where it ends, thanks to the fundamental theorem of line integration. Okay, so let's set this up. Since this is conservative, we need to find little f. Now, I'm not going to repeat that work. That was in a previous video. We need to find little f, and in this case, f of xy equaled x squared y minus y squared over 2. Again, look that up on the previous video where we did that work to find little f. Now, you ready for this? Check this out. So now let's go back and invoke the fundamental theorem. This nasty line integral that we need to calculate all of a sudden just becomes plug in the ending point, which is 1 comma 2, into the potential, minus plug in the beginning point into the potential. That's it. So now I'm going to do that arithmetic. Now watch, I screw up arithmetic all the time, but at least conceptually and calculus-wise, man, this problem's easy. This is great. So yeah, I'm going to plug in 1 and 2 here. So I'm going to get 1 squared times 2, so that's 2, minus 2 squared is 4. 4 divided by 2 is 2, so that's that. Minus whatever I get here. Plug in negative 1 and 4. Negative 1 squared is 1 times 4, so that's 4. Minus 16 divided by 2, which is 8. So 2 minus 2 is gone. I'm going to get negative 4 minus a minus 4, which is positive 4. How about that? That's a lot faster than having to parameterize this curve, calculate the dot product of the field along with the path's parameterization, not just that, but the derivative of that, dot those things together, and then evaluate from some t-value to some t-value. Having a conservative vector field, at the very least, makes the math a lot simpler, a lot more straightforward, right? So you can see why folks love a conservative vector field if you can get one, right? If you can get one, because the math in a conservative vector field, especially calculating work along that along a path in that field, is very easy, compared to what it would be a little bit more just, brute force method by definition. Awesome. Now, another way that this can be thought about is instead of, suppose that finding little f was tough or I forgot how, okay? There's still a nice shortcut method that you can think of. Since this is now, it doesn't matter the path, but you can't find little f, well, you could do it the traditional way, but now you know you don't have to do this path because it's a conservative vector field. So why not start here and just do the straight line connecting the two dots? And then do it like we did in 15.2. In other words, I don't have to take that path because I know it's conservative, and conservative means that, it doesn't mean, but a conservative vector field implies that the path doesn't matter. That I'm going to get the same calculation for the work integral as I do flying around here or just going straight to the point. So in a case where little f is hard to find and I'm in a conservative vector field, you still have an option that's better than dealing with the original path. You just have to do the one maybe straight line path. Or maybe if you like zeros, you do this path and then this path. Right? Maybe that's a simpler way of traveling to that point. Bottom line is, I don't have to take the crazy, undescribable path like that. Okay? Cool. Any questions with that? We doing all right? Okay. I'm now going to do another example using the fundamental theorem of line integration, but this time it's a 3D. So it's going to be 3D. That doesn't make any difference. I mean, there's a small difference. Instead of I and j, we have I, j, and k, right? But the arithmetic and the theorem still holds, whether it's 2-dimensional, 3-dimensional, or 75-dimensional, right? So let's go ahead and do an example on a 3D field. We want to evaluate this line integral again. F dot dr. C is a piecewise curve, smooth curve, from 1, 1, 0 to 0, 2, 3. Okay, and I'm not even going to draw the path, right? Because, well, I guess I don't know this yet. But here we go. The field has been given to me as this. 2xy I plus x squared plus z squared j plus 2y z k. Okay? That's the field, and they did give us a picture of the curve. But I'm going to check to see if this is conservative. Now, I don't know if I did a three-dimensional problem. We only have the two-dimensional test, right? So, time to teach you the three-dimensional test. If the curl of f is 0, then f is conservative. And that's the test to see if a three-dimensional field is conservative or not. It's a little bit more work to show that this is the case. The previous example is just calculate this one partial, calculate the other partial, see if they're the same. So yeah, here I have to calculate the curl, which is it's a certain calculation, right? So let's remind ourselves how to calculate a curl, and then we'll see if this is 0. If it's 0, then this field is conservative. If it's conservative, then we'll need to find the little f, right? And so let's get to it, see what we got. So let's calculate the curl of f. Curl of f is best remembered as doing a cross product. Put the I, the j, and the k down. Put the partial of x, the partial of y, the partial of z. Put that down. And then put the field components here. So the 2xy goes here, the x squared plus z squared goes here, and the 2yz goes here. Okay. All right, let's go ahead and calculate the curl. So here we have I. I'm going to say take the derivative, take the partial with respect to y of 2yz. Well, that's going to be 2z. And that's minus the partial of this with respect to z. Well, the partial of x squared with respect to z is 0. Partial of z squared is 2z. Hey, we're off to a good start. Look at that. 2z minus 2z. That's going to be 0 in the I component. Minus j built in. And now I'm taking the derivative with respect to x of 2yz. That's 0. Minus the derivative of this with respect to z. That's also 0. So that's just straight up 0. Like that. Plus k. Take the derivative of this with respect to x. That's going to be 2x. Built-in minus sign. Derivative of this with respect to y. That's also 2x. And lo and behold, we end up getting 0. See that? So this means that the field is conservative, which means I now know there exists a potential function, little f. Okay? I showed you how to find a two-dimensional potential function with 2 variables. Let's see how it works with 3 variables. So now let's try this. We need to find potential f. Okay. So remember, now what we're saying is that this field is the gradient of some little f. This means that our starting information is the following. We know that fx is 2xy. We know that fy is x squared plus z squared. And we know that fz is 2yz. That's our starting information. We know the partials of little f. Can I reconstruct little f from these partials such that the gradient, right, such that the gradient of that function is the field? Okay? All right, so here's how we start. You start just like we did last time. You're going to take one of these partials and then integrate, right? Okay. All right, so f is going to equal the integral of 2xy with respect to x. Okay. That right there is going to get me, the 2 and the y are constants, and so I get x squared over 2. So the 2's will cancel and get me x squared times y, right? Now, the issue is, what is the plus c here? Well, because this function has 3 variables, and I only integrated with respect to one of them, the constant term is going to be a function of 2 variables. So this could be as bad as some, let's say, g of the other 2 variables, y and z. Right, I integrated with respect to x, and so if I differentiate back with respect to x, I'm going to get 2xy, but this is going to get missed, isn't it? The derivative of that with respect to x is 0. In other words, this is an unknown part of my function f from just this piece of information. Okay? But that's okay. I'm going to fix this pretty quick. I'm going to find this unknown information pretty quickly. Okay? So here's how I'm going to do this. Now, take this, and I want to differentiate this with respect to the next variable, which is y. So I'm going to say that fy equals, what would that be? X squared plus g of yz, but that's going to be the partial of g with respect to y comma z. Okay? That's what I calculated fy to be, right? But I also know what fy has to be. It has to be this. So I'm going to set this equal to x squared plus z squared. Now I have an equation where I can solve for my unknown function. Yeah. Okay. And notice some really good news here. The x's cancel out here. The x squareds cancel out, which is good because this function can't have anything to do with x. It's only a function of 2 variables. It's a function of y and z. So we have gy, y and z equals z squared, right? So I don't know g yet, but I do know the partial of g with respect to y. And it's z squared, okay? Now, since I know gy, let's integrate this with respect to y to get g. So I'm going to say g equals the integral of gy with respect to y. Okay, that's going to be the integral of z squared with respect to y. And so this is going to end up being, well, remember z squared is constant relative to y here. So I'm going to get y z squared plus a function of the last remaining variable, which is z. So let's do h of z. Okay, so I at least unlocked a part of what g is. It has to be yz squared plus some function of z. So let's update what f is. Right, f is now x squared y plus yz squared plus h of z. Okay, so we have that information right now. Okay, now there's a piece of information we haven't used yet. We have not used fz, and we have an unknown function h of z. So to get that, I'm going to calculate fz using this. By calculation, that's going to be 0. This is going to be 2yz plus the derivative of this with respect to z, which is h prime. And now I want to set that equal to what I think fz should be, which is 2yz. And do you see what happened? Luckily, the 2yz showed up, and this cancels because it has a y in it, and I better have nothing but z's left. This tells me, subtracting that off from both sides, that actually h prime of z is 0. Which tells me that h of z is a constant. Let's say capital K for constant there. Okay? So, as you can see, finding a potential function might not be the most straightforward. It is algorithmic. Like, you can just sort of go through an algorithm to find it, right? But it still might be better to do this than it is to parameterize a certain path. This still might be really difficult to do. And so maybe finding a potential function is somewhat easier, to tell the truth. Okay, so let's see what we got. We now have that f equals x squared y plus yz squared plus some constant k. Here is my potential function. This is going to make the integral super easy. Okay, super easy. So let's go sort of review those steps again, because I feel like I've sort of was all over the place here. We start with fx, fy, fc from our field. Right? Start with like the first one. It doesn't matter, but you can start with like one of them. I usually go from x, y, z, right? Start with that, integrate against its variable. So integrate that with respect to x. It's going to get this with a function of two variables. Your next goal is to figure out what this is. To do that, I'm going to differentiate so I can match it up with this. So I'm going to differentiate with respect to y. That got me here. Set it equal to what I know that is. Solve for the unknown function. That unknown function is z squared. The partial of the unknown function is z squared. So I integrate to figure out what g is. That got me this piece. So I got a little bit more information about g. Now I have to solve for that unknown function h of z. To do that, I'm going to utilize my last variable. Differentiate with respect to z. Set it equal to the partial of z. Solve for h prime. Take its integral. And then that's the full understanding of little f. See that? Okay, now it's time to make easy short work of this integral. So this will actually be the quick part. What I'm saying here is that f dot dr, since f is conservative, this becomes little f at the end, 0, 2, 3, minus little f at the beginning, like that. So now I just plug in. Now I just plug in stuff. So let's go ahead and do that. Plugging in 0, 2, and 3 into f right here. Right, and so 0 is gone. Y and z is 2 and 3, so that's going to be 2 times 3 squared. 2 times 9 is 18. So I get 18 from this first one. Minus, plug in 1, 1, 0. 1 and 1 gets me a 1. Z is 0, so that's gone. And so I just get 1. 18 minus 1 is 17. See how the integral was just quick, right? All of the work in doing this integral comes from calculating the potential function. Okay, there you have it. That is what a conservative vector field can do for you in working with when working with line integration, right? You can get this really nice relationship here with a fundamental theorem that it only matters really the starting and the ending point in the calculation of that. That's a huge, huge shortcut. It's a huge, awesome thing there, right? Now, let's see here. This allows me to say something like this. What do you think is going to happen here? What do you think the work is in this conservative vector field? So suppose I have a conservative vector field. Okay, you know it's conservative. I've told you that. Assume it's conservative. And I start here, and I fly around in a piecewise smooth curve like this, come around like that, and then end there. So I start and end at the same place. What is the work done by this field on this particle? Right? If you think a little bit about this, you can do this without knowing much. If you know it's a conservative vector field, you know it's independent of path. You know there exists a little f. This integral, the work integral along this path, is going to be f at the ending point minus f at the starting point. But wait, those points are the same, right? Those points are the same. So what can you conclude, right? So this is going to be, the integral of f dot dr is equal to sum f at the ending place, ABC, minus f at ABC. this is 0. There is 0 work done in a conservative vector field when you start and end at the same place. Do you see that? The parts of the journey that had positive work associated with it, by the time it comes around and hits the ending point again, the positives have countered the negatives, canceling all each other out and getting me a total of 0 in the long run. See that? Does that make sense? Yeah? So we can say if it's a closed curve, that's what I mean when I start and end at the same place. That's what it means to have a closed curve in math. What I can now say is that the line integral in a conservative vector field on a closed curve, that's 0. I don't even have to do any arithmetic. That's just a conceptual understanding of that. Yeah? And so there's all these sorts of things that we can say. Now that we have this idea of a conservative vector field, right? We can say that these are all equivalent statements. If f is conservative, there exists some potential function. That's the same thing as saying that this line integral is independent of path. So the path doesn't matter. It could be a crazy path or a straight line path. Same result. And then third, it means that for every closed curve, that line integral is 0. See that? And so that is basically the end of this section, right? So you want to just practice that. Now, they go through this kind of interesting little thing right here. We have a conservative vector field here, right? And I got to point out this great thing that the book says here. So when presented with this problem, you have the following 3 options, okay? So here's the field. The field's not pictured, but this is how the field works. And here's a couple of paths, right? Here's this circular path. C1 does this sort of semicircle path from the start to the end, right? So it says to calculate this, you really have the following 3 options. You can use the method presented in section 15.2 to evaluate the line integral along the given curve. To do this, you have to parameterize. So they go ahead and do that, which might, by the way, might take you a little bit. And then for this parameterization, it follows that dr is this. And then you plug it in and you get this, and this is the greatest comment in this book, I think. This integral should dampen your enthusiasm for this option. Beautiful. I think that's a beautiful way to say that. It has indeed dampened my enthusiasm for this option. I do not want to calculate this integral. Okay? All right. So, you can try to find a potential function, right? In other words, test to see if this is a conservative vector field, right? If it is, then you can find little f. And maybe that's easy or maybe that's difficult. So they say, well, using the technique demonstrated before, we found little f, and you just plug in the end minus plug in the start, and you get 2. Cool. That's great, right? But there is a third option. Since you know that f is conservative, it's independent of path. And if you don't want to find little f, maybe that's tricky, maybe you can't find a way to find this very easily, well, why the heck are you using this circle path? Why not just do the straight line path? Much easier to parameterize and ends up being very simple. They say of the 3 options, the third one is obviously the easiest. And I would agree, because remember, they hid all the work in finding little f. Finding little f is not the most straightforward, so there's a lot of work missing here, right? So in fact, this is the easiest method, just to say, oh, don't take the circle, take the straight line path. That's easy to parameterize, and then do it the traditional way. Those are all options because the function, the field is conservative. See that? Nice. All right, let's move on. For the physics fans in the room, I'd love for you to read this conservation of energy part. This is connecting line integration and the work integral to conservation of energy and to why we call them conservative vector fields. I'm not going to hold anything responsible for this, but yeah, you can read that at home and see how that goes. All right, let's get to it. This is our last section of Calc 3 and maybe our last section of calculus, yeah? Wow. Okay. Talk a little bit about Green's theorem. Green's theorem is a wonderful theorem that, again, gives us some options in calculating some nasty integrals. Okay, and so I want to present and write up that theorem, Green's theorem. Okay, and then see what sort of benefit we can get out of that. Okay, all right. So, what if you have this line integral that you want to calculate? And sadly, it ends up being that the vector field is not conservative. It feels like you've really lowered your options, right? If the vector field you're dealing with just isn't a conservative vector field, then all of a sudden your calculations are going to be a little nasty. You have to parameterize a thing. You have to really figure out your path and do that dot product and all that stuff, yeah? There's still hope via Green's theorem if you're on a closed curve. Remember, if you're in a conservative vector field, the closed curve, the work integral will be 0. But if you're in a non-conservative vector field, that's not going to be 0, right? And so Green's theorem will allow us to say something about the line integral regardless whether the field is conservative or not, as long as it's a closed curve that we're integrating along. Okay, so here we go. There's going to be a couple words here that I have to describe, but let me get it down first. Let R be a simply connected region with a piecewise smooth boundary called C, oriented counterclockwise. Okay, I'll have to show that in a little bit, but it's oriented counterclockwise. Okay. If M and N, these are those are the components of the vector field, have continuous first partial derivatives, first partials, then, and here's the good part, this line integral, and here it's written in differential form, just like I did in the beginning of this video. But remember, conceptually, this is still the work done by a vector field Mi plus Nj along a curve C. This actually has another way of thinking about it, and the results will shock you. This is actually equal to a double integral over the region of the difference of the partials. Partial n with respect to x minus partial m with respect to y, dA. Now that might not seem like a big deal, and it might seem like it's complicating it. It's like, wait a minute. This line integral is equivalent to some double integral? Why is that easier? Why is that better? Well, I'm not guaranteeing that in all situations it's always better, right? But in a lot of situations, it is better. It is actually better to set up this double integral than it is to parameterize a crazy curve. Sometimes we can really get good use out of this identity, that this is the same thing as this, right? Now, let's talk a little bit about the details. Let R be a simply connected, okay, region. So that means basically that there's no holes in it and there's no separations in it, right? So simply connected would be something like this. That would be a simply connected closed curve, right? And oriented counterclockwise means you go around this way, right? So you're going counterclockwise this way. Now, sometimes the orientation's hard to see. Counterclockwise means that the region inside is always to your left as you travel. right? So the region is always to my left as I travel along the boundary. Yep. So that's the direction you need to go. If you're going the wrong direction, all that does is switch the minus sign. You'd get the opposite of the answer that you have. So you'd get positive number or a negative number, but you'd get the same value. Okay. But they have to pick an orientation, so they set their minus sign, right? So the common orientation that we use here is counterclockwise. Okay. So yeah, simply connected means there's no holes in this, right? Means that it's not separated into like two pieces, right? And piecewise smooth, we've already talked about that. It's smooth in pieces, and that forms the boundary. So the boundary is C. So what this is saying, and this is just miraculous if you think about it, this is a ridiculous concept to think about. What this is saying is that the work done as I travel along the boundary, right, has a connection to the area integral, the double integral, that traverses all the points inside of the region. There's a connection between the boundary of this thing, in a line integral sense, and the double integral, which is traveling the entire inside of this region, if you will. There's a connection between those two things. That just seems almost impossible to imagine someone coming up with that idea, right? And so how cool is that, right? So let's go ahead and do an example. Now, another cool notation, because Green's theorem requires a closed curve, a closed boundary, you might see this notation. This notation is to remind you that I'm not just integrating over any curve C, I'm integrating over a C that starts and ends at the same place. It's a closed curve. So you might see that notation out and about. And it's one of those great fancy notations that a lot of people don't know what that actually means, and it makes you look real smart. And it's like, would you show somebody your work that has a bunch of that on it? People are like, what is that? So yeah, it's cool. It's cool. This is like the thing they show in math movies, right? To show like math is so mysterious and so crazy. And they just show like this in the background and those symbols. This is usually in there somewhere. Yeah, flexing the math game. You got it right. Exactly. Okay. Are you all ready to do the last example of the semester? Oh, that got real. Let's do it. We're going to actually use this Green's theorem, okay? Now, it looks like a lot of notations, but again, do you see the theme of chapter 15 is if you follow the notation, if you understand the language, if you understand the notation, it tells you what to do, right? And so let's see if we can follow the notation correctly, and we will get to a correct answer. All right, so here we go. They want us to calculate the line integral along curve C of y cubed dx plus x cubed plus 3xy squared dy. Okay? Where C is this path. C starts at the origin, and it goes to 1, 1 via x cubed. Okay, so this is y equals x cubed. So it starts out like that. And then once it hits this point, it takes a sharp turn and goes back to the origin as a straight line, like that. Okay. So you can clearly see that this is a closed curve. It is piecewise smooth. It's smooth on this piece. It's not smooth here, but it's smooth on this piece, right? And so it's piecewise smooth, right? There's a finite number of places where it's not smooth, but the points in between are smooth. Okay. Now you might, right, check if this is conservative or not. I'm not going to take the time to do that, but remember that the field associated with this is y cubed I plus x cubed plus 3xy squared j. Right? This is just two-dimensional. So this is super quick. You want to calculate the derivative of this with respect to x, right? And you want to take the derivative of this with respect to y. Notice those are not equal. This field is not conservative. So it feels like all is lost. However, it's not, because the curve I'm integrating along is a closed curve. So Green's theorem is applicable. Let's see if Green's theorem has something to say here. That's maybe easier than having to parameterize curve 1, figure out that, then parameterize curve 2, and then do that separate integral again, and then add up the results. Maybe there's a more straightforward way. Okay. Here's what Green's theorem would say. This integral is equal to the double integral over the region R of this interior. Which is basically saying, can I double integrate in a region that looks like that? This is going back to chapter 14, isn't it? Now let's go ahead and write down the details here. This is going to be partial of n with respect to x minus partial of m with respect to y dA. Okay? That's the right-hand side of Green's theorem, saying that this integral should equal this integral, which is a double integral over r. Let's go ahead and calculate this. What is the partial of n, n's here, with respect to x? That's going to be 3x squared plus 3y squared, right? Minus the partial of m with respect to y. That's going to be 3y squared dA. And oh my goodness, it's almost like this problem was built to do this. I get beautiful cancellation already, and the function I'm integrating, the surface I'm integrating over, is just 3x squared dA. I mean, that's amazing. That's an amazing simplification right there. Now all I have to do is unpack the dA, either as a dy dx or dx dy. I'm going to choose dy dx because, look, I can write little vertical arrows from the bottom to the top and then push that arrow from left to right. That's super easy to double integrate over. That region's beautiful. So I'm going to get the integral of 3x squared. dA is dy dx. Y starts from this cubic function, goes up to this function, which is y equals x. So that's going to go from x cubed to x, from bottom to up. And then the x starts at 0 and goes over to 1. So I've converted my line integral, which looked disastrous, which is over a non-conservative vector field. But it is a closed curve that wraps around a region that's easy to double integrate over. This is the perfect situation for Green's theorem. All right, let's finish this off. Integrate with respect to y. So I'm going to get 3x squared y, evaluated from x cubed to x dx. Plug in the x for the y. I'm going to get 3x cubed minus 3x squared times x cubed is x to the 5th. Integrating this gets me x to the 4, so divided by 4. X to the 6, divide by 6. 3 6 1/2. Valued from 0 to 1. Man, look at that. 3/4 minus 1/2. 1/4. That is so satisfying. Look at that. The last answer of the last example in calc, 1/4. Very lovely. Very nice. All right, so let's sort of recap what we just did, right, with Green's theorem. We had a vector field. I checked out that vector field, and it turned out to not be conservative. Boo, okay? But, like I said, we have a closed curve. And that closed curve wraps around a region that is easily describable using dy dx or dx dy. So Green's theorem is in play. So I can convert that integral into this double integral. In addition, the thing I'm integrating over actually greatly simplified. That was just sort of coincidence, right? So that's an added bonus, if you will. Then I set up that double integral, And as promised, that double integral was pretty straightforward, getting me to the result of that line integral via an area integral. All right, everyone. Well, that brings us to the end. So there you have it. Yeah. I just want to say it's always been enjoyable to teach Calc 3, and this has been no exception. Yeah. Really appreciate all of you out there who've been watching the videos and working hard on maybe an online format that you wanted, or even an online format that you didn't want, but are still working hard to try to learn during these very challenging times, right? And so appreciate that you check in with the videos and that you're doing your work and all that stuff. I wish you all the great success. I hope you're happy and healthy through your future here. And maybe I'll see some of you in differential equations in person in the spring. That would be amazing to see you all there. Some of you are, of course, are maybe already in differential equations or even finished it, but maybe I'll see some of you there next semester. If you haven't signed up for differential equations yet, you probably should. You probably should do that. So yeah, see you in differential equations. Great. Yeah, Christian, thanks. It has been a pleasure. Appreciate you coming to the live. Thank you, live folks, for showing up so often. It's so good to see at least a name out there, like listening and interacting a bit. So that's really cool. But is the same book for differential equations? No, differential equations has a separate book, and I would suggest not buying it from the bookstore. Oops, did I say that? Please find it used somewhere, right? And do not pay $200 for it, please. Yeah, please don't. It is not worth $200. It's not even worth $100. I would probably argue it's not even worth $30, but that's just me. See if you can find a nice cheap version of that book somewhere. Would be my recommendation. Yeah. So anyway, until next time, whether I see you or not, stay healthy, stay happy, and looking forward to maybe when we connect again. All right. Be well. Bye now.